Hello, in this video we're going to continue our talk about linear transformations and matrices. The first thing that we're going to prove is if you have two functions and they are both linear, then their composition is also linear, and matrix of the composition is the product of the two matrices of those linear transformations. Let me remind you of something before I get to the proof of this theorem. So the reminder is that if you have L from Rn to Rm, if that is linear, then that tells you that L of V is equal to a matrix A times V, and we showed that A is unique, and not only it is unique, but also we know exactly what A is going to look like. It would be L of E1 all the way to L of En. And this is an m by n matrix. So again, any linear transformation is of the form L of V equals A times V, where A is L of E1 all the way to L of En. These are the columns of A, and every function of this form is in fact linear. So let's prove this theorem now. Okay, so we know that f and g are both linear, and we want to show that the composition is also linear. So how do we show that the composition is linear? We will show that it satisfies the properties of linear transformations. It satisfies additivity and homogeneity, or we can do the shortcut of L of u plus cv equals L of u plus cl of v. So let u and v be two vectors in Rn. Now, I'm going to look at and take some scalar c. I'm going to look at GOF of u plus CV. So what is the composition? The composition is G of f of u plus CV. That's just by definition of composition. That's how composition is defined. Now, I'm going to write down the inside using linearity of f. So that would be f of u plus c f of v. And the reason for that is f is linear. Now I'm going to use the fact that in fact g is linear. So that becomes g of f of u plus c g of f of v. And this one is because g is linear. So this step goes from the fact that g is linear. And by a theorem, g of u plus cv would be g of u plus cg of v. And these are of course just compositions. So this is GOF of u plus cGOF of v. And I just showed that if I have GOF of u plus cv, it would be GOF of u plus cGOF of v. Therefore, GOF is in fact linear. Now that I know it is linear, I can go ahead and find its matrix. So what is the matrix? If you recall, that theorem told us that matrix of, so let me write it down, by a theorem, matrix of GOF is GOF of E1 all the way to GOF of En. So that's the matrix, because remember that f goes from Rn to Rm, so you would take E1 through Em, you plug it into GOF, and those would be columns of matrix of GOF. I'm going to evaluate the ith column of this, so this is equal to, I'm going to evaluate maybe the jth column of that. So the jth column of this matrix is GOF of EJ. Now, what is GOF of EJ? That is G of f of EJ, which is, so let me actually rewrite that, which is going to be the jth column. Okay, let me write it down. Okay, yeah, so this is just G of f of EJ. So that's the jth column of matrix of GOF. Now, what is G of something? G of something is mg times that vector. Now, what is mg times that vector? that's exactly the jth column of mg times mf. Because if you think about this, if you look at mf was, if you look at mf was f of e1 all the way to f of en. So again, by the same theorem. Now this is by matrix multiplication. Let me explain this. So if you multiply two matrices, if you multiply m sub f and m sub g, the jth column of that would be m sub g times the jth column of m sub f. And that's exactly m sub g times f of ej, which means the jth column of M matrix of the composition is the same as the jth column of the product. So what we just showed is that the jth column of these two matrices are the same. Therefore, matrix of G of F is matrix of G times matrix of F, because they have the same columns. Therefore, they would have to be the same matrices. That equality holds for every J. Okay, so let's look at an example. If you look at the identity matrix, so identity function is the function that gives us x. So the input x gives you the output of x. So that gives us the identity matrix. So the matrix of the identity function, I of x equals x, is given by this identity matrix. The above matrix is called the identity matrix of size n. Okay, so let's actually see that. First of all, I is linear, because if you take I of x plus cy, that is by definition x plus cy, which is of course I of x plus ci of y. So that tells us that I is in fact linear. So since I is linear, matrix of this transformation is going to be I of e1 all the way to I of en. And what is I of e1? That's just e1. What is I of en? That's just en. Which means the first column would be 1, 0, 0, 0. The second column would be 0, 1, 0, 0, 0. And the last column is 0, 0, 0, 1. And that's exactly the matrix that we had right here. So this matrix is called identity matrix of size n, and it's usually denoted by I sub n, or sometimes just I, if it is clear from the context what the size is. These identity matrices are always square matrices. Okay, so we talked about how to multiply matrices. Now we can also talk about addition of matrices. That would be an easier task. To add two matrices, you simply add entry-wise. So the sum of two matrices A and B is defined precisely when they have the same size. So if they don't have the same size, then the sum cannot be defined. So if you have a matrix A11, A1n, AM1, AMn, that can be added to another matrix B11, B1n, BM1, BMn. And the way it's added is every entry is going to be added to the corresponding entry. So A11 plus B11 all the way to A1n plus B1n, so on. So that's how we add two matrices. We can also multiply a matrix with a scalar by just entry-wise multiplication. So if you take a scalar c and multiply by A11, A1n, AM1, AMn, you simply multiply the corresponding entries with c. So all of the entries are multiplied by c. So c A1n, c AM1, c AMn. So you can multiply two matrices. That's something we talked about earlier. We can add two matrices of the same size. We can multiply every matrix by a scalar. Given these, we have these properties. Okay, so there are 4 properties I'm going to go over, and I'm going to present the proof of each one of them. For matrices A, B, C, and a real number R, we have the following. A times BC is equal to AB times C. That's called associativity. The second one is A parentheses B plus C is the same as AB plus AC. B plus C times A is also BA plus CA. A times the identity matrix is A, and identity matrix times A is also A. And then RAB is RAB, which is also A times RB. Notice that multiplication of matrices is not commutative. In other words, AB and BA are different, which is why I had to do these separately. So those are not the exact same thing. One of them is multiplication from the right, the other one is multiplication from the left. Okay, so let's look at the first one. So first of all, in order to be able to define these multiplications, I need the sizes to be of certain form. So let's assume that A is m by n. In order to be able to multiply A and B, I need B to be in m n by k of R, and I need C to be a matrix of, that is, k by L. Now, there are ways to prove this one, but perhaps the easiest way would be to prove what we just saw about multiplication of matrices and linear transformations. So define these linear transformations. Define f from Rn to Rm, g from Rk to Rn, and h from RL to RK. So I'm using these as the matrices of these functions. By f of v would be matrix of a transformation from Rn to Rm would be m by n. So this would be a times v. G of v, this one is in Rk, so it would be n by k, so b times v. Maybe I will change that to w. And h of perhaps x is equal to c times x for all v in Rn, w in Rk, and x in RL. So we're going to define these transformations. Okay, so by the theorem that we just discussed, or we had discussed it in fact in a previous video, by a theorem, f, g, and h are in fact linear. Now I'm going to look at the compositions of these. So I can compose, if you look at these, I can look at h and g, they can be composed. So I can talk about g of h, and then I can compose. So if I draw a diagram here, I have f from Rn, so RL to RK, RK to Rn, and then Rn to Rm. This one is f, this one is g, and this one is h. I can compose f and g and h. If I look at FOG OH, matrix of this, okay, so I know that by the theorem compositions are linear. So by a theorem, FOG, and so if I compose f and g and I compose g and h, they are both linear. If I look at the matrix, so also if I do FOG OH, and if I look at FOGOH, these are linear. Now I'm going to look at the matrices. So if you look at the matrix of FOG OH, by the theorem that we just proved, this is the matrix of FOG times the matrix of H, which is the same as matrix of F times matrix of G times matrix of H. But what is matrix of F? Matrix of F was A, matrix of G was B, and matrix of H is C. Now if I look at M of FOGOH, that's the same as matrix of F times matrix of GOH. This is the same as matrix of F, matrix of G times matrix of H, because matrix of composition is product of matrices. That's something we proved earlier in the video. This is A times B times C, because those functions were defined using ABC. So now if I show that these two functions FOGOH and FOGOH are the same, then that means their matrices are the same. So look at FOGOH at some input. This is the same as F of GOH of that input, which is the same as F of G of H of X. And that's exactly the same as FOG of H of X, which is the same as FOG OH of X. So what does that mean? It means FOGOH is the same as FOGOH. So since these two transformations are the same, their matrices must be the same. Matrix of FOGOH, because we know that the matrix is unique, is the same as matrix of FOGOH, which means A times BC is the same as AB times C. And that proves this part of this theorem. So next we're going to prove the distributive law. Let's go back and take a look. So for this one, I'm going to prove one of them. The other one is going to be similar. I'm going to use a different strategy for proving this one, so that you know, like always for these equalities for matrices, you have different strategies. One of them is using linear transformations and relate them with matrices. The other one is by looking entries of the matrix multiplication. So let's just start with proving the first one. So we want to say A times B plus C is equal to AB plus AC. So suppose A is an m by n matrix with real entries, and B and C are n by k matrices with real entries. Now, one thing to remind you is that, let me just remind you of this. Reminder is that if you take xy and look at the ij entry of xy, that is going to be the sum xil ylj, and L ranges from 1 to n if you assume that x and y are, x is m by n, x has n columns and y has n rows. Okay, so we're going to use that, and this is something we discussed in an earlier video. So we're going to look at A times B plus C, and we are going to look at ij entry of that. So this is equal to the sum L equals 1 to n AIL B plus C times B plus C LJ. This is basically comes from the definition of matrix multiplication. Now, sum of matrix is entry wise, which means this is equal to the sum L equals 1 to n AIL, so BLJ plus CLJ. Now we're going to use the distributive law for just real numbers. So this would be AIL BLJ plus AIL CLJ, which is equal to the sum L equals 1 to n AIL BLJ plus the sum AIL CLJ, and this one also L goes from 1 to n. Now if you look at this one, this is AB IJ plus this one is AC ij. So if you look at these two matrices, A times B plus C, A is m by n, B plus C is n by k. So this matrix is an m by k matrix, and so is the other one, AB and AC, and their sum is m by k matrix with entries in L. And we also showed that A times B plus C ij is equal to AB plus AC ij. So the sum of the entries, because what I found right here is in fact the same as AB plus AC ij. So what we showed is that all of the corresponding entries are the same, therefore these two must be the same matrices. And multiplication from the right, distributive law from the right, would be in fact similar. Okay, so that's the second part of this theorem. Let's look at the third part. I'm going to show one of them and the other one is quite similar. So to prove A times In equals A, I'm going to use the second method, which is the linear transformations, relation between linear transformations and matrix multiplication. So let's take A to be an m by n matrix. That's how we can actually multiply by In from the right. Now consider this function, f from Rn to Rm, defined by f of x equals A times x. We know this is linear by a theorem. Now take that and look at the identity transformation. So identity from Rn to Rn given by I of x equals x is also linear. Again, this is another this was an example that we did. Now if you look at the composition, that becomes linear. So f of I is linear if you take the composition. That goes from Rn to Rm. This is linear by a theorem. Now, and also matrix of the composition is the product of the matrices. So what is the matrix of composition? Matrix of composition is, we know it is the exactly the matrix A, because if you look at FOG, so let me first write it down. Matrix of F is just A. Matrix of M sub I is just the identity matrix. Now if you look at FOI, FOI and F are the same. FOI of X is the same as F of I of X. I of X and X are the same. So this is F of X, which means FOI and F are the same, which means matrix of FOI is the same as A, which means A is in fact equal to A times I sub n. So this guy, this side, is exactly A. So this follows from the properties of the main property that we proved, that matrix of composition is product of matrices. Okay, so the last one, so I'm going to look at the entries of these two, and then I'm going to show that the entries are the same. So if you look at R times AB and look at the entries of this ij, this is R times ijth entry of that, which is the same as R times the sum AIL BLJ. L goes from 1 to n, and I'm assuming that A and B have n column and n rows, and this is the same as the sum AIJ times R times B AIL times LJ, and L goes from 1 to n. This is the same as AIL. This one is R times B, the LJ entry of R times B, and this is the same as A times RB IJ. So as we see, these two matrices, the matrix R times AB and A times RB, have the same corresponding entries, which means they would have to be the same, and clearly they also have the same size. So that completes the proof of this theorem, except for like a couple of parts that were quite similar to what we had done in the other parts. Now, one thing to notice is that matrix multiplication is not commutative. What does that mean? It means AB and BA are not necessarily equal. So now, it could happen that sometimes matrix multiplication is commutative, but it doesn't always happen. So if you look at these two matrices, if you multiply A by B, you will get the first row of this one multiplied dotted with the first column and dotted with the second column. The second row dotted with the other two columns, you get that. If you multiply B by A, the first row of B dotted with the first column of A, that's 0. Dotted with the second column is 1, and then the second row is 0. Even for things like that are pretty simple, AB and BA are in fact not the same. Now, if you have two matrices that AB and BA are the same, we say A and B commute. And that brings me to the end of this video. So I will see you in the next video.